What's up, everybody? Here are the solutions. We're continuing with the exam 1 review, and we're doing the limits and continuity section now. And I'll start with problem 8a. This one we have to compute the limit as x approaches 4 of x minus 4 divided by x squared minus 8x plus 3. And you might think, oh, I have to factor the denominator or something like that. But if you actually pay attention, when you plug in 4 into the denominator, you do not get a 0. Right? Here we have 16, here we have minus 20, minus 32, and then plus 3. It's not going to be 0. However, when you plug in 4 on top, it is 0, so this limit is actually 0. Because we are not having the 0 over 0 case where we have to do any tricks. So that was fairly simple. Let's move on to problem 8b. And here we have a one-sided limit. It is the limit as x approaches 3 from the negative side of x minus 4 divided by x squared minus 9. And of course, when you plug in 3, you get a 0 in the denominator, which means the limit is either plus or minus infinity, and we are interested in finding out which one it is. Now, if I plug in 3 from the negative side, that means I'm plugging in numbers, I'm taking the limit, that are less than 3, which means both the top and the bottom, the top is going to approach 1, negative 1, well, the bottom is going to approach 0, but because 9 is bigger than anything less than 3 squared, it's going to approach 0 from the minus side. This means this limit has to be plus infinity because we have a negative limit on top and on bottom. So that will be the limit here. Let's go on with problem 8c. We have again a limit as x approaches 3 from the negative side, square root of 5x times the quantity x minus 3 divided by the absolute value x minus 3. Okay, we're gonna have to think about it in the same way as we did above. When I plug in 3 on top as a number less than 3, this is going to be approaching this is the same as just x minus 3, right? But the absolute value function, here, I'll write it up here. This is going to be either x minus 3 if x is bigger than 3, or negative x plus 3 if x is less than 3. Okay, and since I am approaching 3 from the minus side, then let's see. So that's positive. If I approach 3 from the negative side, then I am here. I am in this branch of the function. So this is the same as the limit as x approaches 3 from the negative side. I still have square root of 5x. The top doesn't change, but the bottom is not the quantity x minus 3, it is the negative of that. So now these cancel, and the limit should then be negative square root of 15 because of this leftover minus sign. Okay, let's move on to 8d. And here we are considering three functions actually. I'm told that the limit as x approaches 1 of the function f of x is equal to 7. Limit as x approaches 1 of g of x is equal to 4. And the limit as x approaches 1 of h of x is going to be minus infinity. And we want to compute the limit of this combination of functions as x approaches 1 of, here we have f of x plus 1 divided by g of x minus h of x. Now, the part that's going to be really simple is this one, right? This is going to approach 7. The part that's going to be more complicated to think about is over here, and basically what we want to do is realize that h goes to minus infinity, so negative h goes to plus infinity, and g is a finite quantity of 4, so it doesn't really make any difference. We just have 1 over plus infinity, which goes to 0, right? So then this entire limit has to be equal to just the 7 part, because the rest of this fraction is going to go to 0. Let's do 8e. We have the limit as x approaches 2 of x minus 2 divided by x squared minus 4 under the square root, just like so. Okay, and the hint says to rationalize the denominator, so we'll go ahead and do just that. I'll multiply by the square root. So I end up with the limit of, I still have x minus 2 on top, I have the square root part, divided by, I'm going to factor the x squared minus 4 as x plus 2 times x minus 2, so I'm able to cancel that. And this was the limit as x approached 2. And notice now I no longer have a 0 on the denominator, which means I can just plug in. On the bottom I get 4, on top I get, well, I happen to get square root of 0, so this limit is actually just 0. Let's go ahead and do problem 8f. Here we have a limit at infinity, at plus infinity, of the rational function 7x to the 9 minus 4x to the 5th plus 2x minus 13, all divided by negative 3x to the 9th, let's see, plus x to the 8th minus 5x squared plus 2x. And of course, like we learned in class, we're interested in the leading terms. That's these two for the top and the bottom. And notice that they have the same exponent, which means the limit should be just the ratio of lead coefficients, which is 7 over negative 3, or minus 7/3. Let's go ahead and do 8g. We have the limit as x approaches 4 of 1 over x minus 4 minus 8 over x squared minus 16. Now, if I were to do these fractions individually, I would get some kind of infinity limit for both, and of course then I could have infinity minus infinity or something like that, which may or may not necessarily go to 0. So we have to explore this a little further. What I'm going to try and do is I'm going to try to give a common denominator. So this is the same as the limit at 4 of the first fraction needs an x plus 4 factor, and then I subtract 8 all over x plus 4 times x minus 4, which is the common denominator. So this is the same as the limit as x approaches 4 of, well, this 4 minus the 8 is just going to give me an x minus 4 on top. The denominator stays the same, and at this point I can cancel, and then I plug in. This limit is going to be equal to 1 over 8. So actually this infinity minus this infinity in this case happens to equal 1/8. Let's go ahead and do part h, I have the limit as x approaches 0 from the minus side of x to the 1/4. Okay, that's the 4th root of x. Let's think about what the graph of this function looks like. I know that the square root of x looks like that, and since this is a even-powered root, it's going to look very similar. Now if I approach 0 from the minus side, actually I can't, because that's outside of the domain, so this limit does not exist. However, if I were to approach 0 from the plus side, then of course the limit would just be going to 0, that point over there. And that was 8h. We still have quite a few more limit questions, so let's keep going. We have next is 8i, and this is another limit at infinity, where we have x to the 4th minus 3x cubed plus 5x plus 1 divided by x to the 5th plus 12x plus 8. The leading terms here are x to the 4th on top, x to the 5th on the bottom, and since the denominator has a larger leading exponent, this limit is going to be simply 0. Let's do 8j, another limit at infinity of the quantity x to the 4th minus 6x plus 8 divided by 5x cubed plus 8x to the 4th. The leading term on top is x to the 4th. The leading term on the bottom is the second term. They are written in reverse order, so it's not the x cubed. And notice the exponents match, so the limit at infinity is going to be just the ratio of lead coefficients, which is 1 here and 8 here. Let's do 8k. This is the limit as x approaches infinity. I have x to the 8 plus e to the x plus 1 over 5x to the 8 plus 3e to the x plus 12x squared plus 5. And we discussed in class that anytime you have an exponential function, eventually it is going to grow faster than a polynomial, so the leading terms are actually these two, come from the exponential, not from the 8th power of x. Now they happen to be of the same order. I have e to the x on top and e to the x on the bottom, so I am able to take the ratio of the leading coefficients 1/3, and that is my limit. Let's go on to the next one. I have 8l, another limit at infinity of 5 natural log x plus 12 over 7 natural log x plus cosine of x plus 16. Now the cosine of x might be a little bit confusing, but the cosine function stays between plus and minus 1, so it's actually not going to do anything too interesting as x goes to infinity, and therefore the leading terms come from these natural log functions, which do go to infinity as x approaches infinity. They are of the same order, so again I can take the lead coefficient, take the ratio, and that is going to be my limit, 5/7. How about 8m? So I have the limit at infinity 5 plus e to the negative x plus 2 e to the negative 2x divided by 7 plus 2e to the negative x plus 3e to the negative 2x. Now, if e to the x has the following graph, e to the negative x is going to look like this. So as x approaches infinity, e to the negative x approaches 0. Therefore, everything here and here go to 0 as x goes to infinity, and what you're left with is just the 5/7, the constant terms. Let's do another one. 8n. This is the limit at minus infinity now, and I have 1 plus 2e to the x plus 3e to the 2x all over 4 plus 5e to the x plus 6e to the 2x plus e to the negative x. Okay. As x goes to minus infinity, the positive exponentials are going to go to 0. However, this negative exponential is going to go to plus infinity. So I have a constant on top divided by plus infinity on the bottom, which means this limit is actually 0. It is not 1/4 because of this term here. If this had been just an e to the plus x or some other positive multiple of x, then indeed the limit would be 1/4. Let's do 8o. This is the limit at infinity, and I have x squared plus 1 as a square root divided by x to the 4th plus 1. Now, as you plug in very large numbers for x, this plus 1 is not going to matter very much on the top or the bottom, so this is going to behave just like square root of x squared over x to the 4th. We can omit the lower order terms, and for the same reason, whenever we have rational functions like this, we can just consider the leading term. It is the highest power that contributes to the limit as x goes to infinity. So this is the same as just x over x to the 4th, and that's going to go to 0 because the denominator exponent dominates the numerator. Let's do 8p. This is the limit as x goes to infinity of square root of 2x squared plus 8 divided by x plus 5. Now, the same thing is going to happen here. This 8 is not really going to matter very much. So on top, it's as if I had just the square root of 2x squared. And once I apply the square root, this is going to behave just like square root of 2, so the constant stays, x to the 1st once I take the square root over x to the 1st. And of course the exponents match, so I take the lead coefficients ratio, so it's just the square root of 2 over 1, or square root of 2, and that's my limit. So the thing to realize here is once I apply the square root on top, after I ignore the lower order terms, this is acting just like square root of 2 times x to the 1st. Okay, let's do another one that's kind of similar to this, and I think this is the last limit question. And we have the limit this time at negative infinity of square root of pi x to the 6th plus 23x plus 8 all over 2x cubed plus x squared plus 1. I can ignore all the lower order terms. The leading term on top is this with a square root tacked on. The leading term on the bottom is that. Once I apply the square root to x to the 6th, I'm left with x cubed, so they are of the same order. and that means I just take the ratio of lead coefficients, which is square root of pi, since the pi is under the square root, all over 2, and that is my limit. So that finishes off the limit problems. Let's do problem 9 really quickly. We are asked for which values of x is the function f of x equals absolute value of x plus square root x minus 2 divided by x squared minus 9 times x squared plus 4. Excuse me. Now I know that for a rational function, the points of discontinuity happen whenever we have a 0 in the denominator. So it's tempting to say that the set where the function is continuous is the set all reals except for plus and minus 3. However, this is not true because this is not the domain of the function. The domain of the function is restricted by the fact that we have a square root on top, so I can only have x values that are greater than or equal to 2 on top. Okay? So that means what? That means that my actual interval for where the function is continuous is going to be, I start at 2, I omit 3, and then I go from 3 all the way to infinity, and that is where the function is going to be continuous. Okay, so that was problem 9. Let's move on to problem 10. I need a new sheet of paper for that one. Problem 10 deals with the intermediate value theorem. We have a couple of those. So let's see. Let's say we have a continuous function f of x, and I'm told that f of negative 1 is minus 1 and f of 1 is equal to 1. And we are asked whether or not this function can have two zeros inside the interval negative 1 to 1. So let's take a look at what such a function might look like. I know these are 2 points on the graph. If I were to have two zeros, I would have to cross the x-axis once, cross it again to create my second zero, but then I cannot come back to the top point here without adding an extra zero. So the answer is no, f cannot have only two zeros on the interval negative 1 to 1. However, you could have 1 0 because this is okay. You could also have 3 zeros because this is also okay. And in general, you can have any odd number of zeros in the interval. Okay, so that's what's happening here. Now let's do 10b, which is saying to argue without solving for x that there are at least two solutions to the equation negative x to the fourth plus 3x plus 2 equals 0. And the hint says to use the intermediate value theorem, of course. So to do that, we're going to consider the function f of x equals negative x to the fourth plus 3x plus 2. And notice that f of 0 is going to be positive 2. F of 1 is going to be, well, let's see, that's not quite enough. I need maybe to do f of 2 here. So let's take a look at f of 2, because I want to go more negative to cancel these positive terms and dip below 0, have a different sign for my answer than this positive 2 here. So when I plug in 2 into f, I get minus 16 plus 6 plus 2, so that equals negative 8. Now since one of these was positive and the other one was negative, that means by the intermediate value theorem, okay, this is a polynomial, it's continuous, that f has at least one 0. It could have 1, it could have more, in the interval 0 to 2. Okay? And to show that it has at least 2, right? We don't know if it has 2 or more. So far we only know that it has at least 1. We need to think about what kind of function this is. This, for the end behavior, the end behavior of this function is going to be dictated by the x to the 4th term, which shoots off to minus infinity in both cases. So if I know that between 0 and 2 I have some root somewhere and the function is continuous, it's going to have to come back and cross the x-axis again at some other point so that it can shoot off to negative infinity on this side. So since the limit as x goes to either positive or negative infinity of my function, it is negative infinity, f must cross the x-axis at least twice. So it has to have at least 2 roots. And that's how you do that problem. Let's do problem 11, which says, okay, if you know that a parabola opens up, so it looks like that, and it has some zeros at x equal a and x equal b, the question is, for what x value is the minimum of the parabola achieved? And one of the properties of the parabola is that the x value where the minimum is achieved lies exactly halfway between a and b. So it's going to be a plus b divided by 2. That's the x coordinate there. Now lastly we have problem 12, which is another limit question, and this is the limit at plus infinity of x minus square root x squared minus 1. This type of problem uses a different technique than what we've seen before. Here I have infinity, here I have infinity again, so I have infinity minus infinity. But the question is, are they of the same order? What's the answer going to be? Plus infinity, minus infinity? Is it some kind of constant? And before, it was very easy to turn this into a single fraction, cancel some things. However, here that is not the case anymore. So in order to turn this into a fraction, I have to use a trick. I'm going to call this limit, if it were to exist, I'm going to call it the letter L, and I'm going to say e to the L is going to be e to is going to be the limit at infinity of e to the x on top divided by square root e to the x I'm sorry, no, my bad, e to the square root x squared minus 1. Right? So I'm taking this subtraction, when I raise e to both sides, it's e to the top divided by e to the negative part here. Okay, so this is the limit at infinity of that, and let's see, this, as x goes to infinity, it's going to be the same as the limit at infinity of, okay, on top I have e to the x, on the bottom this minus 1 is not really going to contribute a whole lot to my limit, so it's the same as e to the square root of x squared, okay, which is the same as e to the x. And okay, technically we would need to use L'Hopital's rule, but we haven't quite learned how to do that. This is just more of a challenge question and the way we think about these things. So I have this, then what I'm going to do now is well, let's see, I'm going to argue that this is the same as e to the x on the bottom, so this limit should be equal to 1, therefore L is equal to 0. Now, is that really the case? Another way to look at this problem is I could try multiplying by the conjugate. So I could try saying this is the same as x minus square root of x squared minus 1 times x plus square root of x squared minus 1 divided by the same thing, so this is now the same as x squared minus x squared minus 1 over x plus square root of x squared minus 1. So let's see, the x squares are going to cancel. I'm going to have 1 on top, x plus square root of x squared minus 1. Notice the bottom goes to infinity, so the limit is indeed 0. So this is another way to do it, right? Another way to do it, like I was mentioning in class, if you see a square root of something, multiply by the conjugate, and then you know, it should give you the right answer. So this is probably the more precise version of this, rather than this exponential approach here. But either way, you still get the same limit, because over here you had e to the L was equal to 1, so e to what number gives you 1? That L had to be 0. And we did indeed get 0 with the second approach down below here. So that's it for this set of solutions, and I'll also record a video for the derivative type of questions and upload that as well.